Now we are ready to state and prove our theorem on the existence of Haar measures. Every locally compact group G possesses a left invariant Haar measure. Now let's prove this. The idea of the proof is the following. As usual, we'll talk about the idea first. There are two important ingredients in the proof. First, the Tychonoff theorem, which states that any product of compact spaces is again a compact space. And remember, this is equivalent to the axiom of choice. So our proof here will depend on the axiom of choice. And the second ingredient is the Riesz Representation theorem, as I mentioned at the very beginning. The Riesz Representation theorem will be used to obtain the Radon measure, which will serve as our Haar measure. This is obtained from a positive linear functional approximated by the thing we developed for our lemma 2, namely those I sub phis. You will see how we're going to do this. So this Radon measure will serve as our Haar measure. As I said, the core of the proof is to produce a positive linear functional. Let me use the abbreviation PLF. I from I sub phis. This is the core of our proving here. And to begin with, for each f in CC plus of G, let x of f be the interval from 1 over f naught column f to f column f naught, the closed interval. This is compact. Do you see why this is compact? It is not compact simply because we write it in this way, but because something we prepared at the very beginning. So let me emphasize this. XF is non-empty and compact. The key part is that it is bounded. It is closed and bounded, so that it is compact. Because of our answers to the questions raised when we define the Haar covering numbers with respect to functions, when we define this thing at the beginning. Namely, we have recalled this many times before. So let me just write this down. Namely, f column phi is strictly greater than 0 and strictly less than infinity whenever f phi are in CC plus of G. Now, because f and f naught here are both in CC plus G. So this thing and this thing are both numbers strictly between 0 and infinity. So it makes sense to define it in this way. And to be rigorous, I should also say that this x of f is non-empty, not just because of the answers to those questions, but also because this left-hand side is less than or equal to the right-hand side. And that is because we have the following inequalities. The left-hand side, 1 over f naught column f, is less than or equal to I sub phi of f, which, remember, by definition, this is equal to f column phi over f naught column phi. And this is less than or equal to f column f naught. Those inequalities hold because of our lemma 1 part D. Namely the tower property. And I think now I have fully justified why this interval is non-empty and compact. Okay, now we got a bunch of compact intervals corresponding to the functions in CC plus of G. There are infinite many of them. Next, we're going to take the product of all of those intervals. Let x be the infinite product of x of f, where f is taken from CC plus of G. Well, this product could be finite or infinite, depending on the size of our G. But anyway, by the Tychonoff theorem, this product is compact. And since by lemma 1D, as I mentioned above, I sub phi of f is squeezed between f column f naught and 1 over f naught column f. So I sub phi as a function on CC plus of G can be viewed as an element in X, namely in this product space. If you remember how we defined the infinite product in general topology, this infinite product space is literally really the functions from this index set to those xf's, respectively. Namely, each element in X will associate each element in the index set with some element in the factors in this infinite product. But let me write this down so that you can see it more clearly. So this infinite product space is identified with all the functions such that each j of f is in this interval x of f. And I should emphasize this is true for any v in CC plus of G. And now, for each neighborhood V of E, the identity element of G, let K of V be the closure of the following set I sub phi, where the support of phi is contained in V. Be the closure of this set in this infinite product space X. We claim the following. We claim that K of the intersection of Vj's, where j is from 1 through n, is contained in the intersection of K of Vj's, where j is from 1 through n. Namely, if you pull out intersection, then you get one-sided containment. Here, V1 through Vn's are neighborhoods of the identity element of G. Do you see why this is true? I'll let you think about it for a while, but I will tell the answer later anyway. This claim holds because indeed, for any j from 1 through n, this set I sub phi, where the support of phi is contained in the intersection of Vj's, where j is from 1 through n, is contained in I sub phi, where support of phi is contained in V sub j for any j. Now, by our definition, we call that K of V is the closure of those I sub phis where support of phi is contained in V. So, the closure of the left-hand side is precisely this guy. And the closure of this is precisely each K of Vj. Since we have this containment, by general topology, we also have this containment for the respective closures. And because this holds for any j, we can also take the intersection from j equal to 1 to n of the right-hand side. This yields the claim by taking the intersection of the right-hand side. This verifies the claim. Now you might wonder why we are considering this claim. Why are we considering the intersection of those K of Vj's? Remember, our goal was to produce some positive linear functional I from those I sub phi. Now we have lots of sets of I sub phi. How do we produce that I? One way to produce that is to take the intersection of all those sets of I sub phi. But when we take the intersection, we must make sure that the intersection is non-empty. Now, because we have a compact space as a whole space, that results in the general topology, as long as we can show any finite family of closed subsets of such form have non-empty intersection, we can show that by compactness of X, that arbitrary intersection of closed subsets of such will have non-empty intersection. And from that non-empty intersection, we'll produce the I we want. That's the idea. That is why we are considering this claim. We're going to show that this guy will be non-empty, so this guy will be non-empty. And then we'll take the arbitrary intersection of all of such things. So now, why is the left-hand side non-empty? Now, since the left-hand side, which is k of the intersection from 1 to n of v sub j's, which is a closure of this set. It's a closure of this set. But this guy is non-empty because of the Riesz's lemma. Because the intersection of those finite many open subsets, because those v sub j's are all open neighborhoods of the identity element of the group G. Their intersection is again open and contains the identity. So this is a non-empty open subset. By Riesz's lemma, this is in the page 131, section 4.32 of Furlan's real analysis. By Riesz's lemma, the set is non-empty because we can produce a phi that is compact supported and non-zero whose support is contained in this non-empty open subset. So, the intersection of k of vj's, where j is from 1 to n, which contains k of the intersection of vj's, which is non-empty, implies that if you consider the intersection of all the k of v's, where v is an open neighborhood of E, is non-empty by the compactness of X, and page 128, section 4.21 of Furlan's real analysis. This proposition or theorem tells us that in a compact space, to show that the intersection of a possibly infinite family of closed subsets have non-empty intersection, it suffices to show that for any finite subfamily of that infinite family, the corresponding closed subsets will have non-empty intersection. So non-empty finite intersection will imply the non-empty infinite intersection in the compact space. And now, from here, we can do the natural step of taking I0 from this infinite intersection. And our next goal is to extend I0 to a left invariant positive linear functional on CCG. Remember, at this moment, by this definition, those I sub phis are only defined on CC plus of G by definition. Remember, when we define I sub phi, they are all defined on the functions that are strictly positive. Later, we'll extend the definition of I0 to all functions on CCG, not necessarily strictly positive.